Hey, and early good evening to everybody. How we all doing out there? As you can see, the crew is in place. We've got Dave and Rick and the dude. I just want to share with you my outfit for this evening. The dude abides, all right? The dude abides, whereas Dave has the ascot. Rick just looks like the consummate professional. Dave has the ascot kind of lounge lizard look to me. I got my white Russian. We're ready to go. All right. Anyway, so we're going to get started in just about 3 minutes. So I just wanted to say hello to everybody and, just see where we're at. Mr. Whelan, how you doing? How you doing, Stevie? Um, yeah, we got a fun night today. We got huge signups today. We got over almost 300 people registered for today or tonight, and then we'll see how we go. 100 of you are on right now. So that's good. That's very good. I'm glad this thing is proving to be useful for everybody. And we're between Dave and Rick. I think the three of us, we're having a hell of a good time. I would say, and I hopefully you guys are having a good time as well. So that's kind of what it's all about. So anyway, good. As you all know, I'm gonna get rid of Elvis here. I got Elvis Costello going in the background. We don't really need to hear from Elvis anymore, do we?
Elvis is king.
Elvis is king. Did you know that album, My Aim Is True, that first one
I did.
that he came out with?
I
Yeah,
did.
a great record. God.
Yes.
But on the cover, it would look like little checkerboards, but if you look real close, it just kept saying Elvis is king, Elvis is king, Elvis is king.
That's where it comes from.
I thought that was pretty cool. That was pretty cool. Talk about a great debut album.
Yeah.
My man Elvis.
Watching the Detectives.
Watching the Detectives was good. The Angels Want to Wear My Red Shoes. Actually,
Yes.
Angels Want to Wear My Red Shoes. That was my favorite song on the album. Up there, Welcome to the Working Week. I like that one too. I guess there isn't a song on that thing I didn't like. So.
No, they're all good.
Yeah. All righty. Well, let's see. We got just about a minute left, and let some more people get on there. How's everybody doing this week? You guys enjoying your time out there, and everybody staying safe and out of trouble? Mr. Wheels, you're up in Maine. Good for you. I invite you to stop by on your way up or down, but we got to stay 6 feet apart, which for you and me is probably a good thing anyway.
Because yeah. Less time issues happened. Yeah.
The less time we're together, the better off for humanity, I gotta say. Anyway, so we got Bruce. You're doing good out in Michigan. Excellent. Shut your frigging pie hole, says Anthony Reichow. Just getting right in, not
There's
really
Anthony,
wasting
man.
any
Yeah,
time.
rough day today. Yes. Anthony, come on now. Come on. Get one.
Hey, I got a shout out to a fellow Alaskan, Rocky Pavy's on there, so let's say hi.
Rocky, I do the rock.
Rock
Mr.
on, Rocky.
Pavey. Rock on. All right, Rocky. Excellent. We're glad to have it for Taco after lunch in Alaska. So that's awesome. Good to have you on, Mr. Pavey. One of the industry's finest. All right. Not to put anybody else down, but we know Rocky, so he's a good dude. He's a good dude. All right. Mike Miller's on. Very good. Dan Leary, how are you? How you doing, Mr. Miller? All righty, very good. John Messenberg, I don't know if you got the update. Good friend of us all, Dan Foley, was in the hospital over the past week with he's hospitalized with pneumonia due to COVID-19. And when I first heard about it, he was in really, really, really bad way, just really sick. Fortunately, I texted back and forth with him a little bit. He didn't have a lot of energy, but he just said he's feeling better and was hoping to get released. And I guess, was it Monday or Tuesday? Monday or yesterday, he was sent home from the hospital. So Dan's a good friend of us all and a wonderful guy. It was Monday, Steve. Yeah, thanks. Just a real good friend of us all, and we're glad to wish him well and glad that he's back home safe and healthy. So. That's good news. And if any of you guys know of anybody who's ailing right now, again, our thoughts are with you, with your friends as well. So hopefully we're going to come out on the other side of this eventually. We'll see.
We're coming. That's it.
All righty. Well, I guess if we were going to go assign roles here, I'm the dude. Okay. Dave.
You're the dude.
Maybe you're Donnie. I don't know. And did you have a pistol, Rick? You could be the John Goodman character. I don't know.
I'm working on it, but it's taking a while.
There you go. All righty, folks. Well, listen, let's get started here. Couple things just to let you know how this all works. We're going to be yakking away, and we're going to stop every so often for questions. If you guys have questions, type them in. And John, John Messengrink, you had wanted to see if we could open up the microphone for people if they wanted to ask a question. Is that still part of the plan for you?
Yeah, I would think at the end of the presentation where everyone is kind of asking questions. I don't want to interrupt you during the presentation itself, but I would say at the end we could open it up for.
Okay, sure. At the end of the presentation, we'll list the, if you have a question, there's a little thing here to raise your hand, a little button there to raise your hand. Just hit that, and we can see it. And between Dave, Rick, John, and myself, we'll see it, and then we can unmute you. And just if you're ready to unmute, guy, for the co-moderators, you're ready to unmute somebody. Just say, hey, I got so and so here on the line who wants to ask a question, and then you're live in Houston, and then you go. All right.
I guess if you wanted to stop at a certain point and then ask for questions, we could open it up as well. But for time's sake and for continuity, maybe at the end. But it's up to you, John.
Okay. Well, I like I said, I'm good with questions at any time during the program. We'll stop every few slides just to kind of to see what's going on out there, making sure everybody's with us, they understand, and dig in the tempo, and make sure there's any questions that come up during this time, and then we'll just go from there. So we'll play that one by ear because the dude abides, man. The dude abides. All right, the dude abides. Let's get going. All righty, and everybody got their favorite beverage. Here's to you.
Ching chang.
Go After Dark is underway. All righty. We're going to start off with this is part 3. Okay, we've done obviously it's the third of, I'm not sure how many parts it's going to be, probably somewhere between 6 and 8 parts. And tonight's topic, we're going to talk about pipe sizing, air control, and pumping away. It's the logical progression from where we started 2 weeks ago. Basically learning how to do the math, coming up with a BTU load for what it is we're doing. We can't really do much without that number, all right? Once we have that number, then real stuff can actually happen. So tonight, we're going to learn how to size pipe. We're going to learn how to figure flow rates, which is important. A lot of people get kind of funny about math, all right, in hydronics. And there's this feeling that, well, people in hydronics are math phobic, and I just have never really believed that. Math was not my favorite subject in school. I'm sure it might not have been yours as well, but this stuff, hydronic stuff that we're doing is a science, and there's math involved. You want to size pipe, you need to do a little math. Obviously you want to find your BTU load, that's all math, right? But all this different stuff, it includes arithmetic, it includes mathematics. So that's the kind of stuff we want to be able to understand. And you're better at math than you realize. Most guys, so I'm no good at math. In classes, when we talk about math, I see guys just kind of slump over in the body language as, oh crap. But we're better at math than we realize, because as I think we said this last week, math is problem solving. And one of the things we in this industry are really, really good at is problem solving. So understand math is just organized problem solving, step-by-step problem solving. That's why they taught it to us in the first place. It wasn't because in school they had this dying need to know what the hell X was. All right, they wanted to teach us how to think logically, progressively, and chip away at a problem until we reach a logical conclusion. So that's a lot of what we're going to talk about again tonight. So let's just do a quick recap of last week. Where did we leave off? Last week, we talked about the basics of fin tube baseboard, all right? We talked about average water temperature versus supply water temperature when we're looking at these charts, and the difference between 4 gallons a minute and 1 gallon a minute in the output charts. And it says to you which one you should use. Well, only use 4 gallons a minute if you absolutely know the flow rate through that piece of baseboard is at least 4 gallons per minute. If you don't know the flow rate, then use the 1 gallon per minute output line. It makes a bit of a difference. And we also saw what happens to the baseboard output at different water temperatures, and we learned how we could use that for ourselves. Okay, we could use that to our benefit. If you walk into a room and it's got 35 feet of baseboard in it, and you do the math, and at 170 degree average water temperature, it only needs 8. and you got 35, that gives you the opportunity to lower the water temperature a little bit. If you're doing a replacement boiler, it gives you the opportunity to present your customer with a nice high efficiency modulating condensing boiler. It's all good stuff. The other stuff the other thing we talked about, we discussed cast iron radiators, column radiators, tube radiators, how you figure out the output of those things based on height and the number of sections and the number of tubes or columns. And we figured that we learned a concept called EDR, 170 BTUs per square foot at a 170 average water temperature. And as you lower the water temperature, again, the radiation, as with any radiator, the output goes down. And it's just a matter of finding how many square feet of EDR you have in a radiator and what the output is at the water temperature that you're going to use. So all that stuff is we discussed last week. We also talked about sizing radiant floor, and that was about the time that we kind of all lost it. Okay, that we lost both Dave and I during our discussion of radiant floor, and Rick valiantly picked up the gauntlet and ran with it. So good job there, Rick. But we talked about how to size radiant floor. That radiant floor gives off heat based exclusively on its surface temperature. That was the important number, the surface temperature. And everything we do is designed to determine the required surface temperature under design conditions. And when it's warmer than design conditions, obviously the surface temperature isn't going to be as high. And the magic little trick that makes the surface temperature know what to be is the thermostat. When the thermostat's happy, that means the floor is giving off enough BTUs and it shuts off. And we discussed boiler sizing. We discussed the difference between the net HRI or /IBR rating and the DOE rating. And it's basically, where is the boiler going? In a heated area, well, you use the DOE. In an unheated area connected to an older system, you might use the net HRI /IBR output. So it's a little bit different. So there we go. That's kind of where we were last week. So let's get started with this week. And we're going to start this week with the one math formula, in my opinion, the one math formula that you need to know by heart. If you're in this business, this has to be the thing that you know stone dead cold. And the acid test is, can you use and apply this formula as comfortably and as confidently as you use and apply your name and address? All right. If you are in the business of heating people with water, this is not optional knowledge. This is the one thing. It's got to spill out of your mouth comfortably and confidently, like any of your basic personal data. All right. And what we're talking about here in the universal hydronics formula, the universal hydronics formula states that GPM, that's gallons per minute, is equal to BTUH divided by your designed for delta T times 500. So GPM equals BTUH divided by delta T times 500. All right, let's identify the terms. GPM, of course, is your gallons per minute flow rate. We need sufficient GPM to a zone, to a radiator, to a whatever, to deliver the appropriate BTUs. So GPM is your gallons per minute flow rate. If you're a forced air guy, all right, that's like CFM, all right? That's the pulse. It's your gallons per minute flow rate. BTUH, of course, is the required heating load at any given point in time. When we design a system, we design that system to heat that house under design conditions, the quote unquote coldest day of the year. So that's kind of what we're looking at here. So that's your BTUH load. We figure that from our heat loss. Delta T is your designed for temperature drop across the piping circuit. You're designed for temperature drop across the piping circuit. In typical North American residential hydronics, we design to a delta T of 20, meaning the water goes out at 180, comes back at 160 for an average of 170. Or in low temperature applications, it goes out at 120, comes back at 100 for an average of 110. Same thing, only different. All right, it's the delta T we're designing for. As we mentioned last week, there are instances with residential radiant where we may, in fact, design to a 10-degree delta T. So maybe the water goes out at 120, comes back at 110 for an average of 115. That's done for consistency of floor surface temperature. But typically in North America, we're designing around a 20-degree temperature drop. There's nothing magic about it. It simply is what we use. All right. And then 500. 500 is a mathematical shortcut. All right. That comes from multiplying the weight of 1 gallon of water. 1 gallon of water weighs, of course, 8.33 pounds, times the number of minutes in an hour. Now, traditionally, that's 60. There are parts of New York where that hour is shorter than 60 minutes, but now it's typically 60 minutes in an hour. So 8.33 gallons times 60 minutes in an hour times the specific gravity of the fluid. Now, 100% water has a specific gravity of 1. At times the specific heat of the fluid, and 100% water has a specific heat of 1. After all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit in 1 hour. That's a lot of ones. Let's put them all together. 8.33 times 60 times 1 is 499.8. Let's call it 500. Close enough, right? Glycol, boys and girls, is going to complicate things a little bit. The more glycol you put in, the lower that number gets, all right? The weight is different. The specific gravity is different. The specific heat is different. The only thing that doesn't change is the minutes in an hour. So that number gets lower and lower and lower the more glycol you put in. Again, propylene glycol, the heating system type glycol is preferred. Now, when you do that, all right, say a 30% glycol solution might drop that number to say 470, 475. That's a rough guess. There's no consistency amongst manufacturers for this stuff either. Every manufacturer has their own little different mixture, so you got to check the jug. But let's say we drop that, we put in a 30% glycol solution, that number drops to 470. Now it's GPM equals B2H divided by delta T times 470. Your denominator, the number at the bottom of the division sign, is now lower. That means your GPM is going to be higher. Your GPM is going to be greater. The head loss through the piping is also going to be greater. And you may find that you need a bigger pump, all right, a bigger circulator. We'll see how that turns out. But those are the kinds of things you want to look out for. With glycol, your flow rate's just going to go up. That's the way they are. Okay. Very good, very good. Let's see. Yeah, you should be seeing my screen. Are you not seeing my screen?
I see it.
Yeah, everybody should be seeing my screen. I just got a thing here from Jordan. Are there slides or should we be seeing your screen? Now, you should be seeing the screen, Jordan. Hopefully you are seeing that. All right, very good. All righty then, let us continue. Some examples here, an example of what we might want to do with our universal hydronics formula, okay? GPM equals B2H divided by delta T times 500, all right? Let's say we have a zone of whatever, doesn't really matter what it is, a zone of whatever, and we're designing it to a 20-degree delta T, and the load on that zone under design conditions is 25,000, all right? So we just fill in what we know. GPM equals 25,000 divided by 20 times 500. 20 times 500 is 10,000. And you can divide anything by 10,000. That's one of the reasons we use 20. All right. 25,000 divided by 10,000. That gives us a required flow rate for this particular zone of whatever of 2.5 or 2.5 gallons per minute. So it's pretty simple math. So it's the BTU load divided by 10,000. That gives you your flow rate. Another way of looking at it is, is 1 gallon a minute will give you 10,000 BTUs. All right. 2 gallons a minute will give you 20,000 BTUs. However from whichever direction you wish to work that math formula. All right. I always find it easier just because the way my brain works, which is weird, but that's how my brain works, is, just fill in what you know and then just keep multiplying and dividing until you're not left with anything to multiply or divide. So again, BTUH divided by delta T times 500 will give you your GPM when using 100% water. All righty. Any questions out there, Dave and Rick, that we need to take a look at? Turn on your mic there, Dave.
We're all good there. All good so far. Just had that technical glitch on a couple guys just logging in. That's all. All fine.
Okay. Terrific. All righty. Now, how do we use that information? Well, we're going to use that information, that flow rate information, to help us size pipe. All right. Now, remember when we did our last project, we figured the BTU load for the entire house, which was 82,400 BTUs. In this example, I want to just size the boiler piping, the supply and return boiler piping for a cast iron boiler in this example. You'd follow very similar steps with a mod con boiler. to size the header. The boiler piping, the piping coming out of the boiler connecting to the header, that pipe sizing you'll get from the manufacturer. Piping up mod cons, and Rick Mayo can talk more about this as well. Piping up mod cons might be the easiest thing on the planet to do, because they send you a book with every one of those they sell. It's a little booklet that comes with the boiler itself. And Rick, what's in that book?
Lots of pictures.
Lots of pictures, and they are pictures of what?
And they give you how they want that thing piped up. They want to know, whether it's required to be pumped into the boiler or pumped away from the boiler. Manufacturers are pretty, concerned about which way their heat exchanger needs to be piped, and we'll show that. That a lot of them will give you pipe sizes as well based on certain flow. They'll give you pipe sizing and a circulator sizing based on different delta T's that you could run through their heat exchanger. So lots of information from the boiler manufacturers.
It's a magical little book, isn't it?
Mm-hmm.
The answers you seek are found in that book. And one thing we've learned about ModCon boilers is, in general, they don't really work well with your piping creativity, if that makes sense. Follow the instructions and you'll be fine. But let's figure out what we're going to do here. All right, we want to size this pipe. So we got to find the flow rate. What flow rate do we need for the job? So again, it's GPM equals BTUH divided by delta T times 500. The BTU load for this entire house was 82,401 BTUs. So 82,401 divided by the product of 20 times 500, or 10,000. That's going to give us a heat load of about 8.2, 8.3, thereabouts. All right, probably, we want to round up, call it 8.3 gallons per minute. So the pipe coming out of the boiler has to carry all 82,401 BTUs, and the return pipe has to carry the flow rate that's equivalent to 82,401 BTUs to bring that back to the boiler. So these are the train tracks for the whole, think of this as the train tracks at the station, carrying all the trains going out there, right? So we got to figure out what size pipe do we need. And again, pipe sizing is going to be based on flow rate. And for that, we're going to use these pipe sizing guidelines. And I urge you to write these things down and keep them with you. All right. And they're pretty simple. If your flow rate is 2 to 4 gallons per minute, 2 to 4 GPM, we're talking 3/4 inch pipe. And what we're talking about here is copper/black iron. PEX, I want you to look at the PEX manufacturer's flow guidelines. They'll be fairly specific, but this is going to be for your hard piping. So 2 to 4 GPM, we're looking at 3/4 inch. 4 to 9 GPM, or 4.1 technically, to 9 GPM, we're looking at 1 inch. 8 to 14 GPM is 1.25 inches. 14 to 22 GPM is 1.5 inches. So 2 to 4 GPM, 3/4, 4 to 9, 1 inch, 8 to 14, 1.25 inches. There's an overlap there. We'll explain in a sec. And then 14 to 22 gallons per minute is 1.5 inches. Now, where do these guidelines come from? Well, they come from velocity guidelines. All right. They're sized around minimum and maximum fluid velocities. Generally speaking, in closed loop hydronics, we want to design around fluid velocities that are at least 2 feet per second and no more than 4 feet per second. There's your min max. 2 feet per second minimum, 4 feet per second maximum. All right. So what's the difference between feet per second and gallons per minute? Gallons per minute is volume. All right. Feet per second is speed. All right. So if you take a look at this, now I could certainly run 14 gallons a minute through 3/4 inch pipe, couldn't I? Sure. Give me a pump big enough, I'll ram it the hell through that pipe, whether it wants to go or not. The problem is, if I were to ram 14 gallons a minute through 3/4 inch pipe, what kind of problems am I going to have? Let's throw that open to you guys to type in. What kind of problems do you think we're going to have here if I tried to run 14 gallons a minute through 3/4 inch pipe in a closed loop piping system? Type in your answers in the question section and we'll see what you have. Yep, so far so good. Everybody's got it. We got noise, we've got pinholes, we got erosion, all that stuff. Yeah, what's going to happen first and foremost is you're going to get velocity noise. All right, you start running velocities well in excess of 4 feet per second, the pipe's going to let you know it's not happy. That noise is going to sound like anything from a You like that? That's kind of fun with a micro. I'm going, there we go. It's going to sound like that, or could actually you really overcook it, man. You could it'd sound like a freaking freight train going through the house. All right, you really could do that. Now, that is the immediate problem. Someone's going to call up and say, why do I have a freight train going through my house? Or why is it making this noise? That's the first thing you're going to hear. Now, if it's still in excess of 4 feet per second, but maybe not quite enough to cause an objectionable noise, you still have an issue. What's going to happen is you're going to start, water's the universal solvent, folks. You're going to start eroding that pipe from the inside out. All right, and you will develop pinhole leaks over time. Where are you going to see them first? Changes directions, fittings, things like that, where you get that, those abrupt changes in path. But that's going to happen over time. Hopefully, someone argues over or complains about the noise before you get to that point. But that's why you want to stay within these guidelines. Now, what happens? Here's the other end of this. What if I tried to run 2 gallons a minute through 1.25-inch pipe? I could do that all day long, right? I could do that all day long, man, twice on Sundays and not break a sweat. That's a good thing, right? Well, no, man. If you are below 2 feet per second, what happens now is below those velocities, dissolved gases in the fluid have a tendency to turn back into gases, turn back into bubbles. And you may find that you have like babbling brook sounds in your system for no apparent reason. And you've got your air micro bubble resorber whoop-de-doo thing on there and all that stuff, and you can bleed it out and then it'll come back again. And now there are parts of the system, I will say this, there are parts of the system where we want to have less than 2 feet per second. All right, there are parts where we want to have less than 2 feet per second, but your distribution piping isn't one of them. All right, so that's why we have these guidelines: minimum 2 feet per second, maximum 4 feet per second, and we stay within those guidelines. Now, why do we have that overlap between 1 inch and 1.25 inches? That's a good question. Why do we have that overlap? 4 to 9 GPM is 1 inch, 8 to 14 GPM is 1.25 inches, and that's basically the difference, gang, between Type M copper and Schedule 40 black iron. All right, Schedule 40 black iron, I'm kind of limited to 8 gallons a minute and 1 inch. With Type M copper, I can go up to 9 gallons and still stay within my velocity guidelines. And that's really the only one where it's worth worrying about. All right. So in this case, it's whether if you're using Schedule 40 black iron, stick with 8 gallons a minute for 1 inch. But it's copper, you can go up to 9 with no problems. All right. What do we have for questions out there, Dave? Anything pressing?
One of the questions was, can you give an example where you would want that low velocity that you were just talking about?
Yes, I can.
Okay.
I'm not going to do it right now, but I
That's right. That's right. It's coming. Yeah. Yep.
I can most certainly give you an example. I'm just going to do it on my timetable.
That's right. That's right. So that was one of them that came through. Sounds better with the right Russian. That's right.
It does look better with the right Russian, doesn't it? How's that,
Right.
Ken Watson? Is that better? Here we go.
We have a couple hands up, Dave, if you want to unmute some mics, maybe.
All right. I gotta see in there. Sorry about that. I don't have that part up.
I mean, I can do it too.
Okay. Who are you? All right.
Adam Nice, I'm going to unmute his mic. He's got a hand up.
Okay, you're on, Adam. I just want you to know you're on the clock. I got a timer. Let's make it quick. Earth to Adam. Come in, Adam.
Well, he's still self-muted, it looks like. Maybe he doesn't have a microphone or something like that. Or maybe it was just testing me.
Here's a question from Dan Perfetto. I've heard a resonating sound from copper fin tube. Is that velocity noise? I describe that a little better than resonating, I think. Velocity is just going to sound like a whoosh, like you're hearing the water going through the system. And it can be a resonating kind of thing. Yeah. I'd want to know a little bit more about that noise though, Dan, if you have any more info.
Yeah, I've run into that before. Yeah, some of that resonating. You know what? It is sometimes a dynamic of the system itself. It's the length of pipe, it's the pump size, it's the hangers used, where it's rubbing, and sometimes there's just no way to make that noise go away. It's kind of weird. I've minimized it as much as I can on job sites, but not a lot of times where some weird resonations that you get, and it's just vibrations of the circulator and the boilers and the pipe and all this other stuff in between. So it's just really looking at your hangers and how things are supported.
Yeah, there you go. Well, based on our flow rate here of 8.2 gallons a minute, 8.3 gallons a minute, we're looking at 1-inch pipe for that boiler. All right, for the supply, right up until for the supply pipe through the air separator until you start branching off for your zones. And the size of your zone piping is going to be based on flow rate here as well. And then on the return header, once all the pipes come back together, the return header will also be 1 inch all the way back into the boiler. But what happens if the hole on the boiler, on the supply, an old cast iron boiler, what happens if that hole's like 1.5 inches? Shouldn't you have to run? Doesn't that mean, Dave and Rick, you have to run 1.5 inch pipe all the way through to the header? I mean, they put that 1.5 inch hole there, right? Why wouldn't you run 1.5 inch pipe?
Yeah, you'll get BTU stuck in the boiler if you don't.
Well, there you go. Yeah. Now this is one of those things. Size the pipe for the load. All right. Size the pipe for the BTU load.
Indeed.
There's no reason to put 1.5 inch pipe there just because the hole is 1.5 inches. What do you need for BTUs? We had a guy in class once, and I've shared this story many times, where guys said, no, if they put 1.5 inch hole there, that means you got to run 1.5 inch pipe through the header. You got to do it. If you choke it down like you're saying, that boiler's going to make all these BTUs, but you're not letting them out. And I never heard this term before, but I've used it ever since because I think it's brilliant. He said, if you can't let those BTUs out, man, you're going to thermally constipate the boiler. And that's a bad thing, man. And I said, wow, I never looked at it that way, but maybe I guess you will, huh? And I said, thought for a minute. I said, well, that's why the guys down in the lab here, they've been working on a boiler additive. It's a BTU softener, okay? And we call it Thermex Lax, and boom, going to let them BTUs right out. So you don't have to worry. And I swear to God, as my witness, he wrote it down. Wrote it down. So, hey, that's all right. No, you can size it appropriately, size the pipe appropriately. You need 8.2 gallons per minute, 82,000 BTUs. Size the pipe appropriately, size the fittings appropriately, size the air separator appropriately, and now you're starting to control the costs on your job, which is important. All righty. Very good. Very good. So, moving right along. Let's see what else do we have to say here. And if you are at the border of, let's say, 15 gallons a minute, will you still opt for the larger pipe size? It depends. I mean, it depends on what I'm trying to size, I guess, Dragos. That's a really good question. If I can stretch it depends on how important my delta T is. Okay. If I need if I want to go to a 25 degree delta T and I'd rather use the smaller pipe and I can get away with it, then yeah, sure, go ahead. Size it to a 25 degree delta T, that flow rate's going to go down. All right. So yeah, those are things you can play with a little bit. Primary, secondary piping, where you got a single loop primary off of a cast iron boiler. A lot of times people will size that to a 30 degree delta T, and then they'll have different delta T secondaries depending upon what they're trying to feed off of that. So there's certainly reason you could do that. That right. Let us continue. Next in line, we have, if you look at the diagram here, we have our pressure reducing valve, the air eliminator, and the expansion tank. All right. This is just a Taco product that I wanted to show you. I don't know if you guys have seen this before. This is our 3450 combi valve. And Rick, you want to share some info on the combi valve?
Yes, I actually have one of these in my my home, and good thing about this, it's this, you can't see my mouse, but notice from the threads on the right hand side to the face of the portion on the left hand side, it's about the same, almost exactly as a Watts 1156F. So everybody that's been putting those in, that's only getting a pressure reducing valve at that point in time, now can put 2 items in that same space. So now we get backflow prevention and we get pressure reducing with fast fill and with the ability to stop at a certain PSI, all in one nice little package. So,
right, so that is a
great little item.
That's a fast fill and backflow preventer in that one nice little unit. To put it into fast fill, how many guys, let me ask you this, how many of you out there, when you've purged a system, okay, and you've been using a traditional type of of pressure reducing valve where you have a lever that you either lift or put into the fast fill mode, and you're power purging. So you put that thing into the fast fill mode, then you go over to the purge station, you open up the valve and you blow out the air through the hose, and then you close it, and then you got to rush back and take the fast fill out of fast fill mode. How many of you haven't gotten back in time? All right, I want to know for sure. I want you to be honest too. How many of you haven't gotten back in time and have popped the relief valve at least once? All right, and if you tell me it's never happened to you, I'm not going to believe you. Okay, that happens to everybody at least once. The way this thing works is if you put this in the fast fill, you press this button right down here on the end, and it holds, and it stays in fast fill by itself, and it will pop out of fast fill when the pressure reaches whatever pressure you set it for, typically 12 psi. So what you would do here is you'd go open up your valve, push that button in, and then you go into fast fill mode, and you'll power purge. All right, you'll power purge. When you close the valve on your valve station, this thing hits 12 psi, pop, it's out of fast fill. All right. The gauge that you see here isn't a gauge indicator. It's not telling you what the pressure is. It is telling you what you've set the pressure at, which again, if you use the traditional fast fill valve, you have no freaking clue what you set it at other than adjusting it and then looking at the tridicator and adjusting it, looking back again and seeing what you got. All right. This will at least tell you what you've set it at. This entire stem right here is actually a cartridge that is, you can, if you ever have an issue, you can take it out, clean it, etc. So a lot of just some cool stuff there for you to consider. It's a neat product that we have that's got a very unique niche. We also have traditional fast fill / backflow preventer assemblies that you could use as well. But this is kind of a cool product. We're pretty psyched about. There's also boiler trim kits. We have boiler trim kits. A lot of different companies have boiler trim kits, and you can pick your poison here. You can go simple and basic with the scoop and the standard backflow preventer fast fill package. You could go intermediate with the 4900 and the standard package, or you could go deluxe with the 4900 and the 3450. And they come with expansion tanks. Now, all the parts are in a box. They're not assembled for you, but all the parts you see there, the nipples, the fittings, everything is in the box, and you just put it together real quick. So it's a convenience item for you. All righty. Now, one of the things about expansion tanks and pressure reducing valves is they are factory set at 12 psi. Now, they may not get to you at 12 psi, especially expansion tanks, because sometimes, they put them in a box, they put the box in a truck, the box goes up a mountain, down a mountain, it's in a warehouse, it's hot, it's cold. There's a chance it might lose a little bit on the way. Always check it before you put it in. But why 12? What is so special about 12 psi? That's a good question. Why do I care? Why have we picked 12? Why is it 12? It's got nothing to do with Murder on the Orient Express if you've ever seen the movie. But why 12? Why 12? Well, 1 psi is equal to 2.31 feet of head pressure. All right. If you had a column of water 28 inches high, all right, or 2.31 feet high, and you put a little pressure gauge at the bottom, it would read 1 psi. It doesn't matter how big around it is, just how tall it is. All right, so a column of water 28 inches high will have a gauge pressure at the bottom of 1 psi. To file this away for further use, all right, when we size circulators, 1 psi worth of pressure drop, the fluid going through the system, is equal to 2.31 feet of head. So 2.31 feet of head equals 1 psi worth of pressure drop, etc. So just save that for a rainy day. We're going to be using that probably next week. Now, if I were to multiply 12 psi times 2.31 feet of head, all right, 12 psi times 2.31 feet of head pressure, all right, I will get 27.72 feet. 12 psi is the pressure needed to raise a column of water 27.72 feet. Essentially, that's enough pressure needed to fill and pressurize a closed loop hydronic system up to the radiation level of a normal residential structure, all right, with a little bit left over for safety. So that's why we figure 12. If you've got a taller house, where it's maybe you got to go up a little bit higher, maybe you goose the pressure up a little bit. And here's a note, whatever you do to the fast fill, whatever you do to that pressure, that fill pressure, all right, say I go from 12 to 15 on my fast fill, I have to do the same thing on the expansion tank. I have to pressurize that tank up to 15 psi so they're in balance. If I don't do that, the acceptance volume of the expansion tank technically goes down. It becomes a smaller expansion tank, and you may run the risk of creeping up closer to the pressure relief valve popping point. Now, here's a quick pop quiz for you. What pressure do I need to worry about in regards to my pressure relief valve on the boiler? What am I worried about? What number am I afraid of? Okay. What number do we, at what pressure does water start coming out of the relief valve? I guess that's the easy way to ask the question. Type in your answer. I want to see where we're at. This would be your turn, folks.
Oh, it's flying. It's flying.
It is?
Lots of 30s coming in, lots of 30s.
Okay. Yeah, I
There's
see 'em.
people
There they
getting
go.
closer there.
There they go. There they go. Yep.
There
Okay.
they go. They're
There
getting
they
closer.
come. There they come. Yeah, typical is the typical relief valve on a boiler, residential boiler, is at 30 psi. But wait. Ken Wicker has a number that's different than everybody else. He says 27, and he's close. It's actually 27.28. That's when the valve starts to weep. The valve starts to weep at about 27 to 28. It'll blow at 30, but it starts to weep at about 27, 28. So yeah, that's the number you really want to be worried about, okay? Jake Lowry asks, is it true a relief valve is only good for one pop? And if so, why do inspectors want you to pop them during inspection? Dave, Rick, what are your thoughts on that? That's a new one on me. They're not good for only one pop, that's for sure.
I'd have to see that in writing from one of the manufacturers that make those devices, but I would say people doing annuals or popping relief valves just for a second with a bucket underneath there, those go back to working just fine. And again, I'd have to see that from a manufacturer in writing before I would think that they're only good for one shot.
They're good for one shot if they hadn't been used in about 10 years prior. Then you're going to get something jammed stuck inside them. I've run into a lot of times. So if nobody's done anything to them and then all of a sudden they test it, then all of a sudden, yeah, banging out, and it's hard to seal again if, you know, that water's still nasty and everything's floated right up to the top there. So that's what I've seen.
Yeah. Sometimes touching an old valve is always, you always proceed with caution.
Yeah, cringeworthy. Yeah,
proceed with caution because you don't know what's going to, especially a gate valve, but I don't want to talk about it. All righty, let's continue then. All right, hey guys, I want to take a quick pause in the action here because what we're doing tonight is we're giving away a Taco 0018E ECM variable speed circulator. All right, we're going to give one away tonight. It's the new ECM variable speed circulator, multi-feature, multi-function with Bluetooth connectivity, and I think it's the most technologically advanced residential circulator out there. Mr. Holdorf is holding one up as we speak. So this is the Taco trivia question of the night, and this is something we're going to start doing every week. In 1958, Taco, by the way, is celebrating its 100th anniversary this year. Just want to make sure you guys knew that. But back in 1958, Taco introduced the very first wet rotor circulator into the U.S. market. Okay, they introduced the very first wet rotor circulator into the U.S. market. What was the name of that circulator? What was the name of that circulator? Everybody who types in the correct answer will put your names in a hat and we'll select them randomly. Select one at random if you have the right answer. So that is how she's going to work. So very good, very good. All right. So let us continue. And now let's talk about air letting out, air elimination. Air scoops and then micro bubble resorbers. Ours is the 4900 series. Air scoops get kind of a bad rap. They work very well. And what air scoops do is they're air control devices versus air eliminators. They basically let the system run. Does it get rid of every last droplet of air? No. Does it control air so the system can work effectively? Yes. In every respect, yes. 4900 series, Spirovent, etc., the micro bubble resorbers, those things kick the snot out of air. I mean, they just they beat air like it stole something, man. It gets it out of the system. People tend to look at something like that and they say, well, those air scoops, they're pieces of crap. No, they're not. It's just different, man. It's just different. But let's take a look at the differences between the two, and then you can choose what makes the most sense for your jobs. But understand, don't discount the basic air scoop, because it does help you control air in an awful lot of different applications. First things first, air is bad. Okay, we need it to breathe, but inside your system, air has no real job there, and any presence of air is basically detrimental. It has a much lower specific heat than water. Water has a specific heat of 1, air has a specific heat of 0.24. All right. One of the reasons why it's more effective and more efficient to transfer heat with water than it is with air, but that's a different discussion. But the specific heat is about 75% lower for air. So air is an insulator. It inhibits your heat transfer and basically slows everything down. It's not helpful. Air plus water and corrosive materials makes the system water dirty. Okay, causes rust and crap like that. That doesn't help. Get the system water dirty. That kind of can clog up boilers, and it requires a whole other toy to deal with that kind of stuff that you have to put in. And circulators can't pump air. It makes it work really hard. If you ever had a system that was really a lot of air bubbles in it, and you're pumping, you can actually hear that. Hear the pump sometimes go as it kind of tries to move those air bubbles through. It's not a good thing. Okay, the water can move more slowly, so circulators can't pump air very effectively or efficiently. Now here's a thing for you to think about. Why do we put air scoops or air separators or air eliminators on the supply side? Well, let's think about that for a minute. Where's one of those laws? I think Henry's law says the higher the temperature of the fluid, the less capable that fluid is of holding air in solution. Just think about what happens when you put water on the stove, man. All right, you put water on the stove and you watch it, right? The watch pot never boils. Well, it does eventually. You see these little bubblets kind of gathering down at the very bottom of the pot, and then they kind of start bubble, 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 bubble. The higher the temperature of a fluid, the less capable that fluid is of holding oxygen in solution. All right, so let's think about that. Well, where's the water the hottest? Well, in the boiler, but it's at its next hottest coming out of the boiler, right? So if you're going to put your air removal in a system, if you're going to put your air letter outer in a system, it's simply a logical thing to do to put the air letter outer at the point in the system where the air wants to get out the mostest, right? So that's why we remove air on the supply. The water is the hottest, and the bubbles are ripe for the picking, all right? So it's just a way of thinking about it, and that's why we put it there. Let's talk about the air scoop first. And everybody makes these. These things have been around forever. They're simple, they're basic. There's no moving parts, which again is funny. We had one of these sent back to us on a warranty claim once, and it came back and it said NFG, and we looked at it. It was FG. There was nothing wrong with it. It was a fine. It only had 4 holes in it, the 2 big ones and the 2 little ones that we put in. There was nothing wrong with it. It's simple, it's basic, there's no moving parts. You have a small tapping on the top for your high vent and a larger tapping on the bottom for your expansion tank and cold water fill. Basic rule for installing these things. First things first, when you install it, you need to be able to read the writing without inverting yourself, okay? Without moving your head in the 90 degrees or 180 degrees. You have to be able to read it standing up. So that the writing has to be normal. You think you shouldn't have to say this, but everybody here has seen these things installed vertically. You've seen these things upside down. I mean, it's just I'm turning the wrench. That's as far as I could go, In addition, you see that thing on the left that says inlet. All right, that's the Gazinta hole. Then there's an arrow telling you the direction of flow. And we didn't put outlet on the other side. We thought that might be insulting. But what you're looking at here is basically what we would call a left-handed air scoop. All right. If you turn around like so, it's a left-handed air scoop. If you come out of the boiler and you go to the left, you can use this model. If you come out of the boiler and your piping goes to the right, you have to buy a right-handed air scoop. All right. And we charge more for those. I'm kidding. None of that is true. You just turn it around. It doesn't really know. Okay. It go either direction. It's fine. So It's a pretty simple, pretty basic thing, and it's a big open space in the piping. Someone asked earlier, are there spots in the system where you want the velocity to drop below 2 feet per second? Cupcake, you're looking at one right there. All right, that's the point of an air scoop. It's a big open space in the piping. It's a big open space in the piping. The water's zipping around through this pipe, and because that velocity is above 2 feet per second, all the dissolved oxygen is dissolved in that water, frustrated because it wants to be a bubble, man, and it can't be a bubble because the velocity is going too fast, and the pipe is so constrictive, and it just can't be what it was meant to be. It's stuck in something that it didn't want to be. Okay, it's really kind of tragic if you think about it. It's stuck in a mode that it doesn't want to be. Oxygen wants to be a bubble. That's what it wants to be. It doesn't want to be dissolved in water. Now, it goes through the system, and we enter the scoop. All right, we enter the scoop. The scoop is a big open space in the piping. So these dissolved molecular oxygen things that they're repressed, they're all this in that water, then all of a sudden they go into this big open space in the piping. It's like you've taken a weight of 1,000,000 years off of their shoulders. The velocity slows down, and all of a sudden these dissolved molecular oxygen molecules can now become what they were meant to be, and that, my friends, is a bubble. This is what they were meant to be. They become gaseous or bubblicious, if you will. I don't know if that's a word, but that's what they become. And they are literally scooped up, little turning veins in there. They're literally scooped, picked right off of the top of the flow. They're literally scooped up into the upper portion of that chamber, and then they go out the air vent, okay? So that cross section slows the velocity down, big open space in the piping. The veins literally scoop those bubbles up into the upper portion of the chamber, and out they go. Folks, this one on the left here is the absolute important part. You must, when you come out of that boiler and you hit an elbow and you bang a left, you need 18 inches, 1.5 feet, at least 18 inches, 1.5 feet of straight, uninterrupted pipe before you enter the scoop. What that does is basically allows the lighter than water molecule, oxygen molecules, to migrate towards the top of the pipe over that 1.5 feet, so that when they enter the scoop, they'll be up towards the top portion of the pipe. They turn back into bubbles, that vein can get them, all right? So you must have 18 inches of straight pipe leading into that thing. Otherwise, it becomes really a fancy coupling. It's a big green fancy coupling. It's not an air separator or an air eliminator. It's a coupling, all right? And it's a place to hang your expansion tank, and that's about it. Now, again, we've all seen these things with what, a Street 90 or a close nipple, that kind of thing. Those are decorative more than anything else, right? Those are decorative more than anything else. All righty, how we doing out there, gang? How we doing? All right, very good. Any questions we have out there that we need to take a look at, or we still got guys coming up with their oh, so that's just mean. The headphones are messing up your hair, Rick. That's just mean. Ouch, ouch.
He doesn't have the headphones like mine that don't mess up my hair.
Yeah, there you go. There you go. Well, the dude abides no matter what. The dude's hair is not Ken Watson sexy, but it's not bad.
So we did have
Alrighty.
a question come in before.
Yes.
And it was jumping back to our fill pressure conversation that we had going on. And one of the questions that came in was, will pump discharge pressure affect the relief valve, or is it only static pressure? That came from Bill D'Agostino.
It's a combination, I think. If it depends on, well, no, because it's a differential. Pump pressure is a pressure differential more than anything. So I think it's mostly static pressure. The pump is creating a differential. It's adding on one side and not adding on the other. I won't say subtracting on the other, but it's all the pump is doing. It's not creating pressure like a well pump might, you think. It's creating a pressure differential. So I would say it's totally static pressure.
Right.
Does that make sense?
That's the way I would look at it too. Yeah, unless it was such a BAP that it had hair on it.
Yeah.
Now, let me say if let's say we were running at 15 psi.
Mm-hmm.
Okay, that's static, nothing's running, and the pump has the ability. There's several things that have to go wrong here, but if the pump has the ability to pump another 15 psi in there, right? So we're 15 and 15 is 30, right? If you're pumping into the relief valve, you could pop the relief valve off, but you shouldn't be. right? Should be pumping away from the boiler, away from the point of no pressure change, which we're going to get into, right? Is that on
Yep.
on this tonight, or
Yep.
is that late? Okay. So that'll make sense for that question as we start looking at that. Yeah.
All righty. Very good. Very good.
And some of the responses that are coming in saying, yes, that is happening, could, like Rick was saying, and yes, you got to have that perfect alignment to the planets, and, in some cases for it to happen. So it could, yes. In reality, in a lot of chances, it's probably not. Just changing a pump from a 7 to an 8 is not going to make that happen. Correct. Yep.
Very good. Very good. All righty. Let's you're really, you're going to have to go really outrageous in terms of a pump. Absolutely. Yeah. Yeah. All right, let's take a look at the 4900 now. And this is, again, it's a high performance air removal. It's a micro bubble resorber, which really sounds cool, but it's an air killer deader is basically what it is. It's high performance air removal. The Spirovent has them. Everybody makes something very similar. Ours has a couple of different unique things. We use, instead of using like little screens or mesh or like a little copper tube with little brushes on them, we use Paul rings. These are specially designed stainless steel Paul rings that fill that basket. All right, and we've had these things independently tested, and they found that these things will actually remove 3 times more and 3 times smaller mini micro bubbles than, say, some of the others. But there's no real magic sauce here, other than the Paul rings give us 3 times more surface area to grab bubbles without creating much pressure drop. All right, so the pressure drop through that thing is less than the pressure drop through the same distance of similar sized pipe. So again, it's a big open space in the piping. The velocity slows down. Micro bubbles and mini micro bubbles kind of glom onto the Paul rings through the coalescence effect. Then they go up into the upper portion of that chamber, push the float down, and go right out. And again, this will remove air faster than you can put it in, if that's even possible. But that upper portion is, you can take it off if you ever need to. Check the float mechanism. In addition, there's a set screw on that outlet. So if you like to charge your system with air to air test before you fill it up with water, all right, you can simply close that set screw. Now it's an air keeper inner, and you can run your pressure test without having to try to figure out how to cap or plug something. Then when you're done, all right, you just got to remember to open it back up again and turn it back into an air letter router. But that's basically the story behind the 4900. There's no minimum pipe run involved, okay, leading into it. So if space is at a premium, and we're seeing that more and more in mechanical rooms now, right? Remember the old days, you used to be able to have that entire wing of the basement, for your masterpiece. Well, now we got to put 10 pounds of hydronic, into a 5-pound closet. Maybe that 18 inches isn't available to us anymore. So without that space, we need to come up with a different solution. And that's why these things were invented in the first place, was primarily for space. And this obviously does that. And there's no issues with glycol or anything like that. And those Paul rings really do a good job of maximizing the air removal. There was a question there about can you get repair parts for this? Yes, that upper portion of the unit actually is a service part. If it ever needs to be replaced, that whole upper portion is available.
Hey, John.
Yes, sir.
Another thing that sets us apart from most other folks, notice how the top of that is in a cone shape, conical configuration. What that does for us is it gives us a distance. John, if you could put your mouse on where the water level is shown, up right about there. So the distance between there and the mechanism that lets the air out, the cone shape gives us farther distance away from that water. And when that happens, that's less likely to get any debris or dirt or pieces up into the mechanism where it starts to leak. So we have a lot less issues with leaking than some other competitors.
Right. So yeah, this whole portion right here, where my mouse is, that's air. That's actually not water. That's air. All right. And when we push that float down, then we'll let a little bit more air out. Very good. Very good. Okay. Now let's talk about that point of no pressure change, something we can wrap up our hour and then get to open things up for more questions. The point of no pressure change is an interesting place. Now the point of no pressure change, everybody knows this. The point of no pressure change is the point in the system where the expansion tank connects to the system. Okay, in this case, we're looking at right over here. Okay, that is the point of no pressure change. If something, gentlemen and ladies, is called the point of no pressure change, what do you expect should happen to the pressure at the point of no pressure change? All right, let's run that by you guys. Type in, what do you think? If something's called the point of no pressure change, what should happen to the pressure at the point of no pressure change? Type in your thoughts, and we'll move on. But you would think nothing should happen, right? Nothing. The pressure should be constant. Nothing should happen. Right? If you're going to go to the trouble of calling something the point of no pressure change, it is perfectly reasonable to presume that the pressure at the point of no pressure change shouldn't change. Why the heck else would you call it the point of no pressure change? It's illogical to call the point of no pressure change the point of no pressure change if the pressure at the point of no pressure change changes. That would be idiotic. But I'm here to tell you, my friends, that the pressure at the point of no pressure change does change, and it changes all the time. The pressure at the point of no pressure change does change, and it changes all the time. Now, my friends, if the pressure at the point of no pressure change does change and it changes all the time, why, oh why, then do we call the point of no pressure change the point of no pressure change? Who can answer that one? I don't think I could say that again if you paid me $1 million. The reason the point of no pressure change is called the point of no pressure change is not because the pressure doesn't change there. It does change there, and it changes all the time. All right. It's called the point of no pressure change because it's the one point in the system where the circulator can't change the pressure. All right. It's the one point in the system where the circulator can't change the pressure. All right. Let's think about that. There's only 3 things that can change the pressure at the point of no pressure change. There's only 3 things. One would be to add or remove water from the tank, i.e. the system, really. Think about this. The circulator's running, all right? If the circulator's running and the water's flowing through that connection point, could you conceivably have a pump so big and powerful that while it's pumping through the system, it's also jamming some extra water into that tank and changing the pressure? Well, no, it can't. Where would it come from? There's only so much water in the system. In order for the pump to jam water into the tank, it has to take it from someplace else, and there's no place to take it from. So the circulator can't add water to the tank while it's running. By the same token, it can't remove water from the tank while it's running. Where would it put it? The system's already filled with water. So it's neutral. The circulator cannot add or remove water from the tank. The only thing that can would be opening the pressure reducing valve, or opening to add more water to the system, which would add more water to the tank, or opening up a drain and removing water from the system, which would remove water from the tank. So those are the only ways that can happen, and the circulator can't do either of those. Another way of changing the pressure at the point of no pressure change would be to add or remove water from the tank, air from the tank, add or remove air from the tank. Now, the circulator obviously can't do that. It doesn't know how to use a Schrader valve, okay? It can't do that, and it doesn't have arms or legs either, so it's impossible. It can't take air out of the tank. It can't add air to the tank. One thing you do need to be mindful of, folks, is that bladder in the expansion tank is not what you'd call airtight. Through the miracle of oxygen diffusion, you could actually lose up to 1 psi of air pressure charge on the air side of that tank annually, and it would just kind of migrate through that bladder into the system, and you can lose up to 1 psi annually. You let that go on a while, now you have a tank that's small. It's too small, and ultimately you might, for whatever reason, find that eventually that pressure relief valve may blow. So you want to be careful of that. Usually if you're going in for service, check the air pressure on the tank at least once, check the air pressure on the tank. The thing is, you have to take the pressure off of the water side in order to check the pressure on the air side. You can't do it while it's under pressure. So that'd be something that you should include in your service stuff. But the circulator can't do that. And then the most common thing that's going to change the pressure at the point of no pressure change is temperature. As the water gets hotter, the molecules get all excited and they move away from each other. The density of the fluid goes down, the volume goes up. We add more water to the tank, we compress the air. That's why the pressure goes up as the water temperature goes up. Now the circulator doesn't do that, obviously, the boiler does. So that's why it's called the point of no pressure change. What does any of this mean to you? Well, let's take a look. What does it mean to you? It has to do with circulator location. And this is pumping away with a little bit different take on it. Here we've taken everything out of the system that doesn't matter, like the boiler, okay? It doesn't matter. We're pumping towards the point of no pressure change, all right? And we have a system where this little corner right here, forget that looks like a horizontal line for a minute, right here, you have, that's the highest point in the system, and it's 18.5 feet above your circulator point of no pressure change level. Now, again, 1 PSI is equal to 2.31 feet. All right, if you divided 18.5 by 2.31, you'd have a natural, just static 8 PSI pressure differential between the bottom where the circulator is and the highest point in the system, that upper left-hand corner. That by nature is going to be 8 PSI lower just because it's higher. So the circulator's off. It's not creating any pressure differential. If I had gauges on the Gazinda and the Gazata side, we're talking 12 and 12. All right, 12 PSI there, 12 PSI there, and I got 12 PSI at the expansion tank, point of no pressure change, okay? So far, so good. Now, that upper portion is going to be 8 PSI lower. If I had a gauge up there, it would be reading 4 PSI, all right? Now, let's turn the pump on and note that we're pumping towards the point of no pressure change. And this circulator in this example is a small circulator. It's capable of creating 8 PSI worth of pressure differential. And that's roughly about 8.5 feet ahead, maybe close to 9 feet ahead. Now I'm pumping into the point of no pressure change. I certainly cannot raise that pressure on the Gazauta side. So what's going to happen is, in order to create a pressure differential, which is all the circulator cares about, it's creating a differential. It's not creating pressure, it's creating a pressure differential. What's going to happen on the Gazinta side is that pressure gauge is going to drop. The pressure is going to drop by 4 PSI. So gauges on the Gazauta side will read 12, on the Gazinta side will read 8, 4 PSI lower. All right. We're going to get, we have a display of this at the factory. We're going to have it shipped down to Dave, and we're going to show it to you live next week. We'll walk through it and be kind of cool. So I've dropped by 4 PSI here, right here. All right. But I've also dropped by 4 PSI here and here and here and here and here and here. So way up top, I have no pressure. And if I have no pressure, I don't have any pressure differential. If I don't have any pressure differential, it's going to be really hard to have flow. And if I don't have flow, I don't have heat. And if I don't have heat, I don't have a happy customer. What you have here technically might be an air blockage. You really drop that pressure, dissolved gases want to come out of solution. Technically, it might be an air, you would consider it an air problem, but you can't solve it like you'd solve an air problem. You can't go back and purge this thing and purge it and purge it. You're not changing the dynamic any. All right, you basically have a no heat situation. All right, I hope that makes sense to everybody. There's nothing going on up here, and technically it's an air blockage, but it's not an air problem. Air problems look a flow problem. What you have is a flow problem, and flow problems look a lot like air problems. All right, you could put if you were to go put you had a purge station down here at the boiler room, and you put a hose on that, and you tried to blow the air out of that loop. You're not going to get any air. You're changing the pressure differential scenario. All the air is going to go back into solution, and you're just going to be blowing out water. That's a sure sign that it's not an air problem. The number one indicator of an air problem is air. If you bleed that thing and no air comes out, it's not an air problem. It's a flow problem. Now you got to figure out how to solve the flow problem. All right. Now, if we were to pump away from the tank, now we're just basically adding the circulator's pressure differential to the system. And now you can see that pressure differential is going up. The outlet pressure will be going up. We're going to keep that air dissolved within the system, and we're going to have good, consistent, and quiet flow all the way throughout the system and be able to deliver heat. Now, one of the things that happens here, a lot of people are saying, well, you put the pump on the return side. That's wrong. It won't work. It's only dummies put it on the return side. But have we all, my friends, seen boilers that have been working for decades and decades and decades with the pump on the return side? There has to be a reason for that. Dave's raising his hand. Yeah, there has to be a reason for that. Why? Why do these pumps work with the pump on the return side? Well, think about those types of systems. These are older systems. What kind of pumps did they have on the return side? Maybe an old B&G 100 or a Taco 110. Now those are high flow, low head pumps. We're talking 4, 5, 6 feet of head pressure differential. All right, in terms of PSI, 2, maybe 3 PSI worth of pressure differential. It's all those things needed. They were high flow, low pressure loss zones. Putting that pump on the return side, we never encountered this position or this condition, and the system's going to work and work just fine like it has worked for decades. All right, it's worked for decades. Problems arise when that pump finally dies, and the service guys go in and they put in the pump that they were told to keep on the truck for service because it was the only pump they'll ever need, and that's your typical 3-speed pump. All right, that has 3 speeds, man, which is 2 better than 1. All right, that's 3 speeds. It's got low. No one uses low. It has medium. The only people that use medium speed are those with commitment issues. And then it's got contractor no callback mode, also known as ramming speed, speed 3. And you're replacing a big pump. You put that thing on speed 3, give it all she's got, Captain, and see what happens. Well, that's a high head pump. We're putting a high head pump in place of a low head pump. Now we're creating a problem that didn't exist before. All right. So the best way to solve that problem, in my opinion, I'll ask you guys, what do you think if you came across that situation? What do you think the best way to solve that problem would be? You've got a high head pump on the return side of an old system that used to have an old B&G 100 or Taco 110 on there. What's the simplest, easiest, and least expensive solution to this problem? Let's see what you guys think. All right, let's see what you guys think, and I'll move ahead here for your solution. All right, what are we getting some answers in here, Dave? Move it to the supply side. Okay, we could move it to the supply side. A circuit setter, add pressure. Know your pressure drop across the pump, lower the boiler pressure, increase the water pressure, put the right pump in. There we go, ding, ding, ding. I think we have a winner. I'm talking about the fastest, simplest, easiest, least expensive, and most certain solution. We could move the pump to the supply side, but let's remember that system worked for a generation, maybe 2 generations on the return side. So the pump location's not the problem. The problem's the pump. Okay, the problem is we use the wrong pump to solve the problem. That's the problem, right? Say that back to me, Dave. I'm not sure I said that right. Yeah. The problem isn't the problem. The problem is your perception of the problem. That's the problem isn't the location. The problem is the product. It's the wrong pump. It's the wrong freaking pump, right? It's the wrong pump. So yeah, you could move the circulator, but that's repiping the boiler, right? You're basically repiping the whole thing. Let's think a little bit more. I mean, that'll solve the problem. No doubt about it. That will make the problem go away. But let's consider some easier solutions. Could we increase the system pressure? We could. To what? It's a guess, right? And remember, whatever you do to the system pressure, you also have to add pressure to the expansion tank. So if you increase the fill pressure, you got to add pressure to the expansion tank, and you can't do that when there's water pressure on the water side of the expansion tank. So you may have to drain the system, take the tank off, put a little air pressure on the air side, put it back on, fill the system back up with water, increase the water pressure, purge everything, and see if you got it right. And if you didn't, you got to do it again. And then you got to worry about putting too much pressure in the system. So yeah, it'll work. It'll work. It's time. Okay, it's going to take some time.
Just back up one slide so we can see all those on what we're talking about right now. Yep.
Right. Boom. There we go.
There
now, if it worked great for a generation with a low head pump, wouldn't, to me, the simplest and fastest thing and least expensive overall might be to take the old pump out, take the wrong pump out, put the right pump in. Am I crazy?
And you shake it all about.
And you shake it all about. It's the hydronics hokey pokey, right?
Right.
Yeah. I mean, think about it. If it was your mistake, I'm not saying if it was your mistake, you want the quickest, fastest, cheapest, easiest, and surest solution, right? Hey, take the wrong pump out, put the right pump in. Well, I got to eat the cost of the pump. Hey, that's tuition to the school of hard knocks, boys and girls, right? That's just the way it is. If it's the customers, if you're fixing someone else's screw up and the customer's got to pay you for it, well, they want the quickest, fastest, cheapest, easiest solution as well. So they could pay you to futz around for a morning to find the right fill pressure, or you just take the wrong pump out, put the right pump in. Here's the bill. What do I do with this other pump? It's yours, have fun with it. I don't know. Turn it into a planter. I don't know. That there's different solutions. If they want a solution that they can still use the pump they already bought, well, it might cost them more in terms of your time and labor than it would be to swap out the pump. So just something to think about. You solve that problem the way you think makes the most sense. I'm just looking at it kind of logically and objectively, where it's the wrong pump for the job. See, 3-speed pumps, 3-speed pumps are not the only pump you'll ever need. It was a great story when they first came out. Hey, it has 3 speeds. It does all these really cool things. It's the only one you'll ever need. Keep it on the truck for service. It turned out to be false hope. It's a good pump. It does a lot of cool things, but it's not the be all and end all. You got to understand system dynamics, and you got to respect the dynamics of that system, and then put in circulators that make the most sense for that job. All right. It's a nice story that one size fits all. Unfortunately, it doesn't. Just the way it is. That said, everybody sells a lot of 3-speed pumps and people love them, but for the wrong reasons. Personally. All righty. Now, lastly, just out real quick on Henry's law. We talked about this earlier. The more pressure on a fluid, the more gas dissolves in a liquid. All right, and vice versa. So you increase the pressure, the more the dissolved gas stays dissolved, and vice versa. And also colder liquids hold more gas, and vice versa. So think about pumping away then. If you're rebuilding a boiler and replacing a boiler, pump away. I mean, geez, it just makes so much sense, and the benefits are so huge. Just understand, if you're replacing a dead circulator, understand what the circulator is, what it does, and why it's there. All right. So pumping away just makes a lot of sense in regards to Henry's law. We're adding the circulator's pressure right after the air-let or outer. So anything that's still left in the system, woof, you're adding that pressure and you're keeping it dissolved throughout its trip through the system. And that makes the air separator acceptable. The air, the air killer deader, the 4900, makes that less of an issue, but it's still, it's your choice as to which one you choose to use. So, all righty. That trivia answer was the perfecta. So what we're going to do, note the time there, Dave. Note the time. Any answers that came in before 8:13, and when we first found it, just go through, if you want to go through all of those that answered perfecta, and then we'll pull them out and put them in a hat, and we'll pick a winner before we go off the air tonight, if we want to do it that way. All right.
Okay.
I
I
have
gotta go find a
nobody
hat.
on my end that said perfecta, so I might be looking at different things than you, but
All right, I wrote them all
gotta-
down. I got a bunch of names here. I got about 15 different names here written down.
we're looking
So-
at different information then. So
All
I
right.
guess so.
So we
I'm
got
gonna have to go. Now I got to go find a hat.
Yeah. Yes, it was the Perfecta, 1958. Again, the very first wet rotor circulator introduced here in North America. All righty. One more thing I do want to let you know is that Dave might be the world's oldest hipster. All right. He's kind of an Instagram kind of guy. He's an Instagram kind of guy, and he's got these stickers. He had these stickers made up. And if you want a sticker, and if you want to trade stickers, we'll swap stickers with you. But we got these little stickers. We got our 100th anniversary pump sticker, and then we've got a Taco After Dark sticker. So contact Taco Training on Instagram and provide Dave with your mailing address, and we'll swap some stickers with you, man.
Yeah, man. And the ones that I get from you guys, I'm going to be bringing to the factory, and we've got a couple of toolboxes. If you've never been to a factory training class, that I've got lots of room to shove them on. So I'm looking forward to fill that thing up and stop looking at the black on them.
Yeah, because when Dave first came to me with the sticker idea, actually I did tell him to shove them, but he, as it turned out, he had a good idea. So yeah, that's what we have. So, so again, if you want those stickers, so on Instagram @Taco Training, and we'll hook you up with some stickers. All righty. So what's up next for Taco After Dark for next week? Next week we're going to get into figuring flow and figuring head loss. And we're going to start down the path of the finer points of circulator selection. So, the dude will abide next week as well. And we're going to find out how to find the flow, how to find head, and then start looking at pump curves and system curves and understanding that pumps kind of dictate system performance maybe more than we've ever thought. The circulator's in charge because the circulator's going to work on its curve. Whether it's a variable speed pump or a fixed speed pump, the circulator's going to work on its curve. And it's going to tell the system what's what. All right, it's going to tell this. It's not this, you know, the people, oh, well, the circuit system's going to do what the system's going to do. It's kind of a nice thought, but it's very Zen-like, but it's BS. It's not true. The pump's going to dictate what happens within that system, and we're going to look at that next week and really get into some fun advanced hydronics. Yeah, Charlie Masson asks if Dave's a hipster, where's the man bun? Well, Dave's man bun said goodbye a long time ago, as did Rick's. Mine is hanging on for dear life. All right. Okay. Well, let's open it up now. Let's go back and take a look at some questions here. What do we have? And guys, like I said, there's 193 of you still on. We'll stay on as long as you guys want. If you'd like to, raise your hand and ask a question, let's, do that as well. And we'll start addressing these things between the three of us. One of us will know the answer. I know who my money's on. But let's take a look here. All right. Jim Hillpiper says, since higher water supply temps allow for better air removal, is it wise to run a low temp system at high water temp for initial removal of oxygenated air after fresh fill for a certain period of time during commissioning? Jim Hillpiper, you always ask really good questions. And let's go right to Rick Mayo, who's our resident boiler expert.
I've not been asked that question. I would say there are times when you'd run, even like the ModCon boilers are relatively warm. That's in the commissioning of the unit, doing the initial startup of the system, combustion analysis and stuff. Would typically take a boiler to high fire to do that. Maybe that's why we've just all lucked out, but I can't put my finger and say that we should run them hot just to get the air out. I think a good air separator like the 4900 does a really good job at low temperatures as well.
All right, very good, very good. Should we should talk about charging an expansion tank properly, says Al. Al, if you mean by charging it properly, I'm going to presume that you mean and it has to be removed from the system, no water pressure on the air side, or no water on the water side, water pressure on the water side, and then charge it to the temp to the pressure that you need. If that's what you're saying, because if that's what you're saying, then I would agree. All right.
I'll speak to that.
There you go.
I'll speak to that. I think the proper way to do it is when you pull it out of the box, it's a brand new expansion tank. Don't believe what the manufacturer says they pre-charged it to. Just throw that out. Get the temperature up. Let it come to temperature equilibrium, and then put a gauge on it. Find out what it is, how far off what it is from what you want it to operate at under static condition, and then charge the tank or let some air out of it. And then I like to say this, and it's not always acceptable from code to code standpoint, but put an isolation valve on there. That makes it so easy. A little ball valve that if they insist you can take the handle off of, but screw that tank on a valve. And that way it's real easy to check on an annual basis. You could go in and check and see if that thing's lost pressure or whatever, and it's easy to take off the system. But that would be my initial commissioning, was pull it out of the box, brand spanking new, double check and see if it's right for what it is once it comes up to temperature, and then spin it on the system on a valve and open the valve up, take the handle off of it.
Right. And if you remember the picture of our boiler trim kits, we actually had a valve there that came with a deluxe kit that actually allowed you to do that isolation and relieving of the pressure, so you could test that in when it's in operation. So
yeah, if
Yes.
the code wouldn't allow you to do that. Yeah.
Right. You don't want it to just be a ball valve. You need it to be a ball valve that has a drain on it, so you can drain just that couple of ounces of water pressure that's in the tank itself. So you isolate it from the system, and then when you open the drain, it's just taking the pressure off on the water side of the expansion tank. So then you can check the air pressure properly. Because if you just put a ball valve on it and turn it off, well, you still got 12 PSI water stuck inside the tank. So you got to have that that drain port too. So just like the like what we have in the fill kits. Yeah, I mean in the trim kits.
Very good, very good. Will Taco offer an expansion tank valve kit like Webstone, other than the one that's in our boiler trim kit? I don't think we'll be offering it as a separate item. It's just included in the kit, just like our expansion tanks. We're not selling expansion tanks as separate items for residential applications. We make big honking ones for commercial ones, but it does not appear that I don't think that's going to be one that we're going to be offering for sale, because there's so many others out there. Do you recommend reading Pumping Away for someone new to hydronics? Yes. And even for someone not new to hydronics, yes, absolutely. For $20, it's maybe one of the best reads out there. It's a little dated. It was written in 1990, but the basics, the fundamentals endure. So yeah, absolutely recommend it. Dan's a genius at this kind of stuff, and making this stuff accessible is a true gift that he has. So yeah, I absolutely, and any other books that he has too, well worth getting. He's done a great gift to the industry. Let's see, what else do we have? In a modern hydronic system, does it make any sense to leave house water on connected to a properly filled system? I guess on not valving off the fast fill. Is that what you're talking, Benjamin?
That's what it sounds like.
Again, yeah, and there are different codes, right? There are different areas that say you cannot have the system connected to, the house. Once it's filled, you got to disconnect it or turn a valve off. And there are others, like when I grew up, I did my business in Massachusetts. You had fast fill, and the water was always on, just in case there was something that went wrong in the system. The fast fill pressure reducing valve would add water to the system, so you would never dry fire. So, so some people say, well, if you have a leak, then you're going to leak forever. He says, yeah, but then if you don't, you dry fire, you could cause the thing to blow up. I mean, or cause a fire, cause something serious. So it's a matter of which degree of safety. So again, your guys' feelings.
Practicing what I preach. If I walk out to my boiler right now, there's absolutely no water hooked up to it. So I want to watch it, and I want to make sure if I ever do have a leak, I have in fact, in mine, I got a 30-pound pressure relief valve, and at 15 pounds is where I leave my system. And as I drive into the garage, I can see it. I always know it's there. If I ever start to go down, I go out and try to find the leak. I don't want to let that makeup water go into the system. Okay. As most of you know, we've got ModCon boilers out there. We got pumps. We got apparatus within the system that doesn't want that fresh makeup water that brings along with it all that particulate. And so you want to know if you have a leak. You don't want to just let it. As John had mentioned, code requirements. Well, there's other ways around making sure that you have the ability to have pressure on the system. So we do these things called Glycol pigs, where you use an oversized expansion tank that allows pressure on the system with pressure reducing valve. There's, of course, all kinds of little apparatus that pump pressure into the system, but only so much, that sort of thing. That's my 2 cents.
Yeah, and the other part of this is I think Steve Whelan mentioned, there's a reason we have low water cutoffs too. So yeah, for you, if you're not connecting to fresh water, to city water, you got to have a low water cutoff on there to keep that thing from burning dry. Yeah. Okay, the questions are coming fast and furious. I love it. I got
one before it disappears. Thought it was a good question to ask. How do we set the system pressure when we have a fill at the bottom of a 4-story building, but the expansion tank is the top? What system pressure? What would we do there?
I don't think it would matter. I think you'd still need the same fill pressure, because you still got to get the water up there, right? And it's got to be pressurized. That's my thought. I mean, we're not. Yeah, that's a good question. That's my thought. Rick, what do you think?
I'd have to pencil it out and calculate it. Rich Medeiros actually has a little training on this commercially, because they do that commercially sometimes. So again, normally we tell them where to put the expansion tank, and it's not at the top of the system if the boiler's at the bottom. So we'd have to do some research on that. But Dave, take note of that. I can't see that question on my end. So
Okay, it
we'll
disappeared.
get
We
an
came in
answer.
about 10 minutes ago.
We'll get an answer. We'll get it through Rich Medeiros, who's our local PE, and we'll get you an answer.
That said, I know a contractor out in Colorado who only thing he would do would be slab on grade radiant jobs. You know, with a you use a water heater or a boiler up above you. Generally, it was a water heater. That they were very, very low temperature systems, so the temperature rise of the fluid was very, very small. And he would not install an expansion tank. He actually did the math that says, I don't need an expansion tank. The water's not going to expand all that much. It's a low temperature system. All right. I don't need to pressurize because everything is below grade. All right. And any thermal expansion of the water was absorbed by the PEX tubing that he was using. So he had a built-in expansion tank. I said, that's brilliant. How much money does that save you per job? He said, about 40 bucks. I said, okay, great.
That's not a license to do it wrong, as far as I'm concerned. I've had the same thing happen. I've shut my expansion tank off just for the reason I was telling you, forgot to turn it back on, never had the relief valve go off. My miles of 5/16 tubing was taking the expansion of the system. I never had an issue, but that's not a reason to do it wrong, in my opinion. So.
Yep, there you go. There you go. I've always thought that you can't oversize an expansion tank. Cost aside, is this true? Yes, that is true. It's impossible to, you can't oversize. You know, as long as the pressure's right, you're not oversized. You can undersize, but if you oversize, yeah, you could put in, a number 60 tank when you only need a number 15. That's just money. But putting in a 15 when you need a 60, well, that's wet floors. So yeah, that's not going to work. So
I got a curveball to throw out there just for fun.
Alrighty.
How many people think that when you size an expansion tank, actually, I got sunshine coming in through my window. Can you tell that?
It's not dark
You folks are in the dark. Anyway, how many people think that when we size an expansion tank, we're sizing it purely for the acceptance of the expanded water coming into the tank? And I won't wait for answers on that. Guess what we're sizing expansion tank for? It's the air volume of the tank. When we talk gallons, we're talking air. We're not talking water. So think about that. That kind of tips you on your head to say, you know what? I never thought of it that way. I thought all I'm worried about is how much water is expanding into the tank. No, when we start talking about the size of the expansion tank, we're talking about the amount of air that can accept that expanded volume so that you don't pop the relief valve and the pressure doesn't get too high. So that's one of those, things that scratch your head. You could tell I've been scratching my head a lot. So think about that and look into it. And I think you'll see where we're coming from there.
All right, very good, very good. And what else? We had another question up here. Sorry. Did John work for Worsbo around the end of the 90s or early 2000s? Guys? Yes, we all did. Every one of us. All three of us did. Yes, we all did. And we've all moved on. So yes, Mark, we all did, and we are now all at Takeo.
The band's almost back together.
The band is almost back together. That's right. That's right. Is there a minimum distance fittings need to be from the inlet or outlet of a circulator? That's a good question, guys.
On the suction side or the inlet side of the pump, kind of an industry standard is we like to see a nice long piece of pipe. It goes back to that whole thing about 10 pipe diameters, 12 pipe diameters. We want laminar flow into the suction side of a circulator, generally speaking.
Very good. And on the other side?
You can do anything you want on the other side, but again, a nice length of pipe on the other side would be good. We see all these little pre-made boxes that have all this stuff shoved in, like John mentioned, 10 pounds of hydronics in a 5-pound box. They can never get these, the rules of primary, secondary, no more than 4 pipe diameters between the tees. We like to see 8 pipe diameters coming into the first tee, 4 pipe diameters on the exit side. So a lot of times you can't get that in these little boxes. And so the question is, does it work? Yeah, it works, but it doesn't follow those general rules that we like to see with laminar flow coming into the tees, laminar flow going out. Same thing applies to the circulator.
Right. Yeah. Is it works? Is it ideal? There's always considerations, and there's always stuff like that. Yeah, absolutely. Absolutely. What is the future of polymer pumps from Taco? Will they become normal or exception? I guess you're talking about composite bodies, Corey. Is that where you're going with this? I mean, our 00 series ECM circulators have a composite casing around the motor that's kind of injection molded over the motor, makes it double insulated. So that in that respect, yeah, that is the future. That's the present, and should be the future going forward. In
Well, I think
terms of
he's also looking at the 006E too.
right, talking about the
Yeah.
volute. Now the volute's a little bit different. The casing's a little bit different. There are long-term pressure and temperature things that need to be taken into account. And then there's also, is it going to be flanged? You know, you get that 3-foot wrench and 4-foot cheater bar to tighten those bolts down. You've got durability issues. So there are different things going on. Our 006E3 has a composite body with union connections. So that's something we are doing and will continue to do. So the bigger answer is I couldn't tell you, but you know, the short-term answer is we have some of both, and as you know, as manufacturing methodology and composite materials improve, as the durability and the temperature plus pressure thing for long-term testing can be overcome, you may may very well see that. I need another White Russian. You may very well see something like that. Hey, there's a beverage here. The dude abides. Why are there expansion tanks specifically for radiant, and is it possible to oversize an expansion tank? Yeah, we answered the second part already, Derek, that basically no, you can't really oversize it. Why are there expansion tanks specifically for radiant? Now I've seen those, and I've always kind of wondered the same thing. What makes this thing radiant specific as opposed to hydronic specific? And are they using those terms interchangeably? You know, that's a question. Is it called a radiant tank for marketing purposes, so you'll buy it for your radiant systems, or is it called a radiant tank because it does something specific? I tend to look at the former rather than the latter. Rick, you were nodding your head.
No, I don't know. I have seen tanks specific for radiant, and I haven't looked into it close enough to know for sure. My guess off the top of my head is they might put an oxygen diffusion barrier material like a EVOH within the actual butyl bladder that might help the non-barrier type systems. That's a guess. Don't take that to the bank.
There you go. Dave, who bought your sport coat?
I did.
I like
I do wear them once in a while. Yes.
I like the matching ascot / pocket protector. I thought that was pretty cool. You know, here you guys, I'm going full dude though. I got my bathrobe, you know, now you don't want to see you want to see the shorts? Here we go. I got my flowered shorts on, man. I'm ready. I'm ready to go because the dude abides. Have you tried peanut butter whiskey in your White Russian? Oh, that might make me want to start drinking again. Wow. I'm one of those guys, you put peanut butter on anything and I'll eat it. And you could put it on a shoe and I'll dine on that swine like crazy, man. I'm a peanut butter freak. I love me some peanut butter. So you put it in anything, on anything, around anything, and I'm going to consume it. So I'm not sure that really is germane to the discussion, but you brought it up, Corey, all right? Does Taco manufacture radiant manifolds? No, we do not. We do not, Brian. A lot of people do. Stuff like that we look at and say, you know, are we going to bring anything new or unique or beneficial to the table? And if we can't, then it's just a Me Too product, and then it becomes a price issue, and then there's no point to it. Let's say Jeffrey Burke, air control versus air elimination, compression tank versus bladder. Is there a question in there?
No, that is just the right statement there.
There
Yep.
you go.
You know, when you look at the differences between your expansion tanks that you have a bladder or the one sitting up in the ceiling, one is air management, one is air elimination. Exactly right. Yep.
And again, I'm
never mix them up.
No. Yeah, here's one thing. Yeah, if you have a compression tank up in the rafters, Do not put in a 4900 Spirovent or micro bubble resorber. Those things go hunting for air, and they will eat the air out of that tank in no time, and you'll have a waterlogged tank in no time. So yeah, don't mix them up. Don't mix them up. So yeah, air control / compression tank, air elimination, bladder tank. Now you could definitely have a bladder tank on a scoop. That works just fine. That works just fine. Very good, very good. Another one from Marco. When you pipe the circulator off the primary header, do you need to be at least 12 inches away from the header? And when you pipe the circulator off the primary header, do you need to be at least 12 inches away from the header? All right, I'll throw that to you guys.
I think that's talking about those pipe diameters on the suction side, so we get a laminar flow into the inlet side of the pump. I think we've already addressed that.
Okay, very good.
Yeah. And I would also look at that. I mean, if we're looking at a primary secondary piping, then that's a different story, as in where you put your closely spaced tees to the next set of closely spaced tees, where you want to be 12 inches at least away to the next set of tees possibly. So that's another idea. So if you can, Marcelo, clarify what you're looking for there. If we've already answered it, then we're good to go.
Very good. Can you overcharge the air side of an expansion tank?
Well, yeah, if it's more than the water side, yeah, you don't want to be more than the water side. You know,
Right.
You want to keep that equilibrium going on. So yeah, you don't want to put too much in there. You got to make sure what the proper water side is. You don't want to go over on the air side, because then you don't have that acceptance level. You're not going to have that water, that extra water volume come into the tank itself if the bladder's too strong.
Yeah, it's just the thing is they must be the same. The fill pressure and the air charge on the air side, they must be the same. And that's kind of where you want it to be. All right, very good, very good. Boom. Let's see. What is the name of the YouTube channel? You answered that. Mechanicalhub.com. This recording and all of the recordings from parts 1 and 2 are on Mechanical Hub's YouTube channel. So if you just go to YouTube, type in Mechanical Hub, go and subscribe to their channel, you'll see you'll see these you'll see all of the videos there. So that will be there for you. All righty. Who doesn't use glycol in their systems? All of our systems in Saskatchewan and Alberta have glycol. Well, glycol is a good thing. What does glycol do? Glycol has one huge benefit, one extremely wonderful benefit that is the whole reason for using it. And what would that be, gentlemen?
So it doesn't freeze.
It doesn't freeze, right? That's the best
No
thing about
slush.
it. It doesn't freeze.
Let me clarify. I think I know, I might have talked to this guy already, but so there's two columns when you look at your glycol manufacturer. The one I grew up with was always Dow, and they probably make the base model propylene glycol for a lot of other manufacturers, but that put their name on it anyway. Look back at your manufacturer. You always have two columns. You have a column that says freeze, and you have a column that says burst. Okay, so what do those mean? Does everybody really know what those mean? I'll say this as a general statement. You never need more than 37% glycol, propylene glycol, if you're worried about the pipes actually expanding to the point of bursting. Okay, I'll say that again. You never need more than 37% glycol if you're worried about the pipes expanding to the point of bursting. If you want to go look at the freeze column's talking about crystallization of the liquid within the system. If I'm doing cooling, if I'm doing, air conditioning, I'm running really cold. What about process piping, where I'm actually taking a fluid that's really, really cold and running it around the system for one reason or another? Let's say I'm trying to move 20-degree glycol, and I don't want it to crystallize. I don't want it to turn into a slushy. That's what they mean with the freeze column. So look at your glycol manufacturer, look at both columns, determine which one's right for you.
All right. And in most cases, the bursting and the slushy thing, you're looking, you don't want the pipe to burst is really what you're looking at.
Right.
All right. And that's indoors. Outdoors, typically with a snowmelt system, they're looking at a 50-50 solution anyway, because
that's if you want to try to push the fluid around in a really cold state.
Mhm.
And absolutely, then you're designing for that. But the thing is, when you're actually melting snow, what will the temperature of the glycol be? That's a question, right?
Yeah.
So they're saying under design condition, if the glycol is going to be 130 degrees, then you size it around that. Otherwise, you're saying that's the same way when we do heat losses for a house, we don't size it based on the initial startup load. You know, that could be millions of BTUs on a cold slab. You see where I'm going with that?
Right.
You don't use that. You use a design condition. So again, if you're going to always be pumping really, really cold glycol, then go ahead and use the cold glycol numbers. But otherwise, use a design condition state.
Right. And I mean, glycol has a lot of other impacts on the system. I mean, again, in terms of figuring your GPM, okay, water is thicker, it's heavier, it's more viscous, it doesn't transfer heat as well. So
Right?
you have those challenges, and those all have to be taken into account. You're going to have higher flow rates and higher head loss through the piping system when you use glycol. So those have to be taken into account. And as glycol weakens over time, it becomes very aggressive and it starts to eat shit. So you've got to worry about that too.
Got to maintain it. Yeah.
It's got to be maintained and checked, and you got to do your pH test. So yeah, there's and you know, Alberta versus New Hampshire, or versus, you know, Pennsylvania versus Washington D.C. Where do you live, man? That has a lot to do with it too. That has a lot to do with it too. Would the composite design be conducive to chilled water applications such as geo? Oh yeah. You're talking about, Dave, you already answered that, not specifically, mostly for open systems. You're talking about the circulators, specifically the composite design. Is that what you're talking about there, Jim? Let me make sure you're right. Can a Delta P pump be built on the same platform as the 0018E? I wonder if we've ever thought of that. That's all I'm going to say to that one, Mike.
Everybody say at the same time.
Do you guys make a glycol feeder system? No, we do not. That's not one of the things that we make, unfortunately. What's the velocity of a swallow carrying a coconut? Steve, get the quote right. What is the velocity of a laden sparrow?
Hey, John.
I got to get it right. What is the airspeed velocity of a laden swallow? African or European? I don't know.
Hey, John.
Yes.
Back to that question on, I think he's referring to the only composite volute that we have is a 0063. The lowest temperature we could run on that is 36 degrees Fahrenheit, 2 degrees Celsius. So yeah, I suppose you could do cooling with it.
Sure. All righty. Can you overcharge? Dave Harris asked that question about 4 times. I think we've answered it 4 times, but and Dave's left. But no, yes, you can overcharge. You can charge it to the burst beyond the burst pressure of the expansion tank based on the manufacturer. Yes, but your fill pressure on the air side of the expansion tank must always be equal to your system fill pressure. All right. If they're not, the pressure in the tank's higher than the system fill pressure, you've got a smaller tank and you run the risk of approaching that 26, 27, 28 PSI we were talking about earlier. So those are the things that's the answer to the question. I think we've answered that about 3 or 4 times already. So very good. Will you be covering low loss headers versus other hydraulic separators, sizing them also? We're going to be talking about buffer tanks a little bit later on, and a buffer tank's just a big low loss header hydraulic separators. To me, those are 2 words for the same thing. All right, it's just somebody calls them a low loss header, somebody calls them hydraulic separator. They're basically the same idea. We're actually going to talk about it in terms of buffer tanks and when you might use one. So that will be covering that at probably number 6, number 7, maybe of the series, in terms of what they do, why you might want them, and how to size them. All right, and when you might need a buffer tank as opposed to a hydraulic separator / low loss header, compared to maybe just primary, secondary, your basic moose antler piping. So we'll be discussing that in a subsequent session, Jordan. So good question. All righty. I forget, but on some jobs, they reduce the piping to the pump, let's say from 4 inches to 2 inches at the circulator flange, but this is okay because of something to do with velocity. If you do that on the inlet side, you're kind of asking for trouble, aren't you? Reducing the pipe size going into the circulator. Rick's shaking his head.
No. a lot of times, just like we were talking earlier, we don't size the pipe to the boiler based on the boiler inlet. We don't size the piping coming in or out of a pump based on the connection size of the flanges. That's a real short little distance that has, or I should say it this way, that doesn't have the same velocity restriction that a piece of pipe does. A piece of pipe is where we start getting freaked out if we're up around 4 or 5 feet per second or above and beyond that. We can go for higher velocities at the flanges, at that bell reducer going down in there.
Gotcha.
We're not worried about that. We're worried about the pipe that's generally seeing all that velocity at one time. So that's why you see what you're seeing. It's just that, if I need a pump that it's 100-something GPM and there's a 4-inch pipe going to it, that pump might have a flange that's 2 inches, and it's okay. So just get as close as you can to the connection at the proper size for the velocity limitation. So.
Very good. Very good. All righty. So we got some more questions here. Graham says better heat transfer and freeze protection. Graham, if you're talking about better heat transfer with glycol, we'll probably disagree with you because glycol just doesn't transfer heat as well as water. No. But we will go along with freeze protection though. So, but it's not better heat transfer fluid. Let's see. The question about expansion tanks. Zilmit's Radiant hydronic expansion tanks have a polypropylene liner to prevent corrosion due to oxygen entering the system.
Aha.
Aha. There we go. Regarding Radiant, that's a Radiant expansion tank. Very good. So if you use a barrier tubing, however,
don't need it.
Not the issue. I remember back in the old days with Radiant, that was one of the things where guys they're saying, oxygen diffusion corrosion. Remember when it was actually considered, there were people that thought it was a myth, that it really didn't exist?
Or European marketing ploy.
Yeah, European marketing ploy. Well, that obviously that went away a long time ago. But I can remember having a discussion with the guy way back in the old days, and he was convinced that boilers aren't failing, man. This is BS. Boilers aren't failing because we use non-barrier tubing all the time. Boilers aren't failing. Yeah, we got to replace the expansion tank every once in a while, but that's just normal. I said, no, it's not normal. That's where it's happening. Where you would see oxygen diffusion corrosion first would be at that point where the expansion tank connected to the system, because that was where the metal was the cheapest, thinnest, and least noble. And there are guys that say, well, yeah, they go in and work on something, and they might accidentally nudge an expansion tank, and a couple days later, poof, the thing would blow off, and mass quantities of water would follow. That was where you were seeing it first, at the expansion tanks, pinhole leaks and corrosion right there. Cast iron boiler, it takes a long time to eat through cast iron, but by the same token, cast iron boilers are not meant to be sacrificial. It's not like an anode rod, So yeah, that was where we first saw them. So very good. African or European? Swallow. I don't know. I saw John Cleese perform live about 2 months ago. It was in Worcester, Massachusetts, and it was at this big concert hall, and they had a screening of Monty Python and the Holy Grail, the full cinematic version, which was a great movie to watch with a live audience. It's funny to watch on TV, but put it back in a theater, and it just becomes hysterical. And there's so much in that movie to miss. But after the movie, John Cleese and his daughter came out, and they did a panel discussion. They were taking questions from the audience that would text them in on Twitter and stuff. And it was just a wonder. The guy's like 80-something years old, but just a sharp wit and a really funny guy. So that was a special night. James Winslow, thank you. Where's Elvis by Dan Holohan. Does PP pipe have an O2 barrier? Aquatherm. That's a good question. I'm not terribly familiar with Aquatherm. You guys? I mean, it's used in boiler piping.
Call the polypropylene folks. They'll tell you what their diffusion rate is. So you can take that.
Yep. Very easy answer to find there. You just give them a buzz. All righty. Terrific, guys. Hey, thanks for the questions. I don't know if there's anything we've missed, but thanks for the questions. And again, this is just it's been a lot of fun these past 3 weeks, and we got another 5 weeks left. So we really look forward to seeing you guys in next week. So we got 115 of you online here. So Yeah, any more questions, please just shout them out. We don't have any place particular to go, do we? I know I don't. Dave's all dressed up like
I
he's
got
ready
a
to
full
go on
bar,
the
man.
town.
I'm not going anywhere.
Yeah, and every time we've mentioned oxygen diffusion, Dave's been taking a shot. I don't know if you've noticed that. You know, Rick's in Utah, so I don't know what kind of fun you can have out there in Utah on a Wednesday night. But
The only place I might need to go is the bathroom, but other than that,
other than that,
good.
there you go.
if you hear me gurgling,
Yeah, we'd
If I
like it if
gurgle?
you excused yourself if you were to do that.
I might have to do that.
Hey, John,
Yo,
are we going to announce the winner of the trivia contest here, or are we going to do that later?
well, Dave, do you have a?
To rip everything apart right now, I'm thinking that either we do it later during the week or we can do it during next week's class as, that's an opportunity too. So, because now I got to rip apart the paper. I got to find a bucket. I'm down in the office. There's not that stuff around. So
You see Dave saying he doesn't want to go to the effort to satisfy that.
I
this
could,
week.
but
Thank you,
now
Dave.
you're going to be
Yeah.
all sitting there waiting for me now. So I've been busy answering questions and stuff. I'm
Yes.
sorry.
right, so
I think let's do an announcement sometime during the next couple of days.
Yeah, we can do it on Instagram, social media, et cetera.
Awesome. Well, that's a great prize to give away. So thank you.
Yeah.
Is
It'll also
Takeo
be a reminder for next week's class too to
There you
register
go.
again.
Here's a question from Anthony. Is Takeo going to get into the legal marijuana market? No, we're going to stay in the illegal marijuana market, Anthony. What the hell kind of question is that?
Anthony's had a long day today. Yeah.
Yes, he has. Dave is increasing system pressure. Yes, he is. Yes, he is. Yes, he is. All righty. Well, hey, okay, here's another one. Very good. If you have a boiler loop and a primary loop, can the expansion tank be on either loop as long as it is before the circulator? I'm not sure I understand the question, Derek. I'm just thinking if you're going to put an expansion tank on a system, put it near the boiler, because again, that's where you're filling the system, et cetera. Am I understanding the question properly?
Yeah,
You know what
primary,
I said?
secondary. Where do you pipe? Where's the best place to tap it into the system? Primary, secondary piping or boiler, loop, moose antlers, things like that. Yeah, where do you drop it in? I think that's what he's thinking.
Send me a
Okay.
picture.
Yeah.
Then I'll answer
Picture-
the question.
A picture's worth a lot here, Derek. If you, Rick, why don't you, Dave, type in Rick's email address into that answer section for Derek, and then they can get together. Because that's a good question, and we want to find out. But I tend to think inside the box in certain. As you can tell from my apparel, I can think outside the box with the best of them. But when it comes to certain things, I'm an inside the box thinker. If I don't have a compelling reason to move an expansion tank, why I can't come up with a good reason to move it. Why would you move it? If it's just simple to me to keep everything really close to the boiler, keep anything that needs service within a space like that, that's easily accessible and easy to isolate, and keep it close to the boiler. So all the stuff I got to work on is right in front of me. That's to me a good thing. I don't know as I'd want to mess with that unless I had to. So I guess if I'm understanding your question, Derek, and if I'm not, please pardon me, but that's the way I tend to look at piping up a boiler. Is let's keep everything I got to work on in one spot, and then we'll deal with the rest later. Okay. I've always wondered that also on the moose antler side of the system, or the moose antler side of the system, or the system side. Okay. Now, with a ModCon boiler, where do you put the expansion tank? Again, I'll put it on the header, right? And keep all my stuff, that I have to work on the header. After the boiler goes into the header, then moving off to, let's say, the left, I'll put, air separator, expansion tank, cold water fill, circulator, then the zone valves, and keep them all on the same side so they're all easily accessible and serviceable. I think that's again what I'm thinking as well. All right.
I'm also thinking about the other components that you're putting in the system. So where are we tapping in that expansion tank? To the air eliminator, right? So if wherever you put that air eliminator, make sure that's in the right spot to do its job, as in get the air out. So, and if we're looking at moose antler style piping, we're not necessarily representing that little piece of pipe coming out of the bottom of the boiler itself and tying into the T's. And we drop in that air eliminator over here. What about this pipe? Well, a lot of the boiler manufacturers are already putting a little vent sitting up on top to catch that little bit of air that might throw in there too, right? So, you know, they've got a little 400 vent sitting up on the top there. Let the air eliminator, you know, that we have out there, the 4900, pull it out of the system itself. That little bit that gets in the boiler, let that little 400 vent pull it out of the boiler.
Christian Garcia is asking, will you guys send certificates? Do you guys want certificates? We can do that. That's pretty simple to do. I'll just include it in the attendees follow-up email. So yeah, if you want a certificate, we're good. You know, that's very easy to do. So yeah, I can do that. Do you, John Messenbrink, are you still there? Do you have any issues with us doing that? We can certainly do that. I think John fell asleep. Oh, there he is.
I have no issue with that. That's fine.
Okay, terrific. Okay, do circulators require minimum linear space before it or after it? Do closely spaced tees require minimum space before the next set? We kind of discussed that a little bit earlier. The answer is kind of, yeah, it's a good idea. Sometimes if you don't, is it critical? It's not ideal, but it's still going to work just fine. How about in a primary, secondary, when you've got closely spaced tees? And then you have further down the line another set of closely spaced tees. What do you want for distances between those? I've always gone 8 inches.
Well, okay, it's 8 pipe diameters coming into the first tee. Is, you know, and so you're saying this, let's get the tees as close together as we can.
There we go.
Okay? So if we come out of something that's already in a laminar flow pattern, we don't need the full 8 pipe diameters. So we could actually do 4s, 4, 4. Again, the more the better. These numbers that we give you, the 8 coming in and a 4 going out, those are absolute minimums. So the more the better. So if you could get 8 and 8, do it. If you get 12 and 8, that'd be better.
Sure.
So anyway,
Yeah.
those are the rules.
Yep. Again, for me, the way I look at it is I visually keeping them separate, so I know these go together, and these go together. You know, if there's a reason to put them closer, then you may need to. But you know, typically, you know, if I'm thinking about a cast iron boiler, a big old primary loop, you've got all the room in the world, basically. That as much, you can take as much room as you need. I guess that might be a better way to put it. All righty, cool. Well, we're starting to slow down a little bit. Mr. Whelan's still with us. Lewis, thank you, great class. Thank you, Lewis. Appreciate you guys coming. Boy, we're going on 2 full hours here.
No.
This is awesome. So guys, thank you so much. And we still got 96 attendees online. That's pretty cool. So you guys just want more of, you know, of this little boy band here. I don't know, what are we going to call it? What are we going to call ourselves? We're going to do a boy band, you know. I think
Let's not ask for suggestions right now. That's not going to be.
I'd say
2 hours of this.
I'd say the dude and his follically challenged. No, maybe not. It's late. I can't think of a good one either.
Yeah. It's too long. The Taco Trio. There it is.
Taco Trio. Yeah, I'd say
The triple threat.
the triple threat. Yeah, there we go. Say goodnight,
triple
John. I'm sorry, I'm all empty. Just so you know, all right, this was almond milk and nothing else. It was a virgin White Russian, if you will.
Okay. Mine was a martini though. Mine
Yours
was
a
a
martini.
martini. Yes, it was.
Rick, what did you have in there?
Actually, that was a Caucasian.
Caucasian?
Yeah, what you were drinking.
Oh, it is milk.
Hey, the dude. No, the dude.
The dude.
Calls it a Caucasian.
It's a Caucasian. It's a glass of milk. There you go.
Mine was actually it's called a Mayo Rita.
A Mayo Rita.
Yeah.
That sounds good. I like that one.
Special
What's a Mayo
recipe.
Rita? It's a family recipe.
Special recipe.
Special recipe. Very good. Very good. All right. Now we're still down to 87. This guy just either they can't get enough or they fell asleep and haven't logged off yet. That could happen.
So no questions.
We could be falling asleep here. Thank Anthony says, great hanging out with you guys, especially now. I think we should call you guys the Corona Tritet.
Trifecta.
The Corona Trifecta I'd go with. All right, the Corona trifecta. Now that's a good band name. I like that. I like that. Oh, here we go. Are we allowed to use the air letter outer or the air letter inner? Those are not those are not trademarked. They're copywritten, but they're not trademarked. So your use of those terms is a little, it's loose. You may be able to use them under certain circumstances with proper attribution. All right, there you go. All right, very good. That worked. Great job. Thank you. Hey guys, thank you so much. I think we'll say goodnight. We'll say goodnight now, and I really appreciate everybody being here. John, thank you once again for putting this thing on. It was awesome, and we really appreciate the opportunity. And I certainly hope we didn't take too big of a bite out of your evening, sitting there kind of babysitting the Corona trio here.
This has been great. Good turnout. Thank you all for joining in, and look forward to next week, man.
All right.
Yeah, this was a fun time tonight. I had a good time tonight. I don't know, maybe it was the martini talking, I'm not sure, but it was still a good time. I greatly appreciate everything that Mechanical Hub has done to put this together and get it out there so we can share the message as we're all hanging at home and trying to keep it normal and still hanging out with everybody. I mean, I just miss getting out there and seeing people right now. So that's been the hardest part. So yeah.
Yeah, so thank you everybody for the gift of your time, and hope it was worth it, and we will see you all in 7 days.
Catch
Peace
you
out,
then.
everybody. The dude abides.